Good morning and welcome you all to this session of the course on fluid machines. In last class, we discussed the concept of specific speed, which originated from the principle of similarity, and we recognized the different similarity parameters, non-dimensional parameters, which are the similarity parameters of fluid machines, from where we derived an expression for specific speed, which are also the similarity parameters and their physical implications. Now, in this class, we will start describing from this class onward different hydraulic machines. Now, first we will start with an impulse hydraulic turbine. We start with an impulse hydraulic turbine, which the very simple type of impulse hydraulic turbine was developed near the end of 19th century, and the person who contributed a lot to its development is named as Lester A. Pelton. He was an American engineer. And following his name, this impulse hydraulic turbine, which we will describe today or we will discuss today, I will describe today, is known as Pelton turbine or Pelton wheel. Pelton turbine, or sometimes is known as Pelton wheel. Now, the Pelton turbine in its simple form, as you see, is represented by principally by a rotor. This is the shaft on which a large disc or wheel is mounted, which executes a rotating motion, this direction, a rotating motion, angular velocity omega. And on this large disc or wheel mounted on this shaft, there are number of spoon shaped buckets which are uniformly spaced over the periphery of this disc. These are the spoon shaped bucket or spoon shaped blades. These are usually known as buckets. They are usually known as buckets. These are actually the blades, buckets. They are mounted on this disc, on the periphery of the disc, uniformly throughout the periphery of the disc, the spoon shaped bucket. The shape of the bucket is like this. If you see a view from this and end view, a view from here, this, or a view like this, or a view like this, if you see, if you see a view like this, you will see a shape like this. This is the spoon shape. Is symmetrical two halves. There is one splitter which divides the flow into two halves. This is the two halves. This is the typical spoon shaped. And there is one or more nozzles which are fixed, which directs a water jet with high velocity to hit this bucket, which hits this splitter ridge, and the splitter actually divides the flow into two equal halves, these two sections of this spoon shaped bucket. And this nozzle is a fixed one, and at the inlet of the nozzle, liquid enters at very high pressure because of its existence at a very great altitude. From great altitude, the liquid comes via a pipeline and comes to the base of this nozzle at high pressure, and this pressure is converted into high velocity by the nozzle, and this directs a water jet, high velocity water jet, to this bucket or this spoon shaped blades, and this executes rotary motion. Thus, the power is developed. So, this fixed nozzle is the stator part of this turbine, and this is the rotor. Now, this is an impulse turbine because of the fact, you see, that the entire pressure at the inlet of the nozzle, the stator part of the machine, is converted into velocity. This is because the jet is ejected into open atmosphere, and therefore, there is no cashing needed as such for the operation of this turbine. Casing may be needed so that water should not go out, okay, to actually splitting of water outside, prevent that, casing may be needed, but for operations casing is not needed, which means the buckets are exposed to atmosphere, the jet is exposed to atmosphere. That means the stator part of the machine, that is the nozzle, issues a water jet with high velocity but at atmospheric pressure. So, when the flow takes place in both the halves of this spoon shaped bucket, the pressure is throughout atmosphere. So, there is no change in pressure, pressure remains atmospheric pressure. So, therefore, by definition it is an impulse turbine, and at the same time the turbine is a tangential flow type, because the direction of flow in both the halves of this spoon shaped bucket is in the tangential direction of the rotation. You can see a better view of this if you see a picture like this. I show you how does it look in a diagram. Please, you see this diagram. Well, you can see this thing better. This is a practical, this has been taken from a real Pelton turbine or Pelton wheel that operates in a hydraulic power stations. You see, this is the shaft, here it is mounted, this is the huge, the large disc, and this is the spoon shape, this is your spoon shape bucket. This is the splitter. So, water strikes here and it enters here and goes out like that. So, it is divided equally in two halves. So, water jet strikes here and it is flowing along the blade in or along the buckets in both the directions. So, therefore, you see these are the spoon shaped bucket as I have shown you in the other picture, and here it is very clear. So, if you see the water inlet and the outlet, the fluid inlet and the outlet in both the halves, they take place both inlet and outlet at the same radial locations, and the flow direction is mainly tangential. This direction is the tangential, the rotation is in this direction. So, therefore, this direction and the coming out direction is almost tangential, that is tangential flow, and inlet and outlet is at the same radial location. Inlet vary with the radial locations depending upon this height of this or this width of this bucket. Similarly, the outlet at different point vary, but for any point at any section, if you consider of this bucket, inlet and outlet is at a given radius. Usually, the speed of the bucket is specified at the central plane, that means this central line, that means this line, that means the central line of the bucket. That means bucket has a width in this direction at the central line. That means we calculate the linear speed by multiplying the angular velocity with this radius at the central plane. Now, one thing should be clear, that inlet and outlet does not vary in their velocity, that is the rotational velocity of the blade, and they are at the same radial locations. And this way the Pelton wheel works, the jet strikes here and they glide along the spoon shaped buckets equally in both halves and come out like this. This is a typical thing, and this thing rotates. This is the shaft. This is the vertical shaft. This entire rotor, or it is known as Pelton wheel, with the disc and with the spoon shaped buckets mounted on it, rotates in the horizontal plane. Okay. Now, if you come here, you see that this is the same thing that is described by principle, it is like this. So, therefore, it is impulse action, it works on impulse action. Now, let us draw a diagram, that means as you have already seen the Pelton wheel in a better picture. Now, you can understand that if we see a sectional view like this, if we cut it like this and see a sectional view like that, that means if I cut this, the perpendicular direction, if I see, it will look like this, as you have already seen it, and now you can appreciate this. It is like this. the bucket is like this. This is the splitter ridge, this is the bucket, and the water jet is directed like this, and this is the plane of the wheel, plane of wheel. This is plane of wheel. This is the water jet. This is the water jet coming from the nozzle, and it comes here and it is divided into two parts. Before that, let me tell you that the number of buckets are usually little more than 15, and it depends upon the specific speed that I will describe afterwards. It is usually little more than 15, and it is inversely proportional to the specific speed of the turbine, and the number of water jets and accordingly the number of nozzles are usually fixed. This is little more than 15 the buckets. It is usually 2 for horizontal shaft and 4 to 6 for vertical shafts. These are for number of jets and the number of nozzles, and this is more than 15 for number of spoon shaped buckets, which depend on specific speed. Now, we concentrate here. The water jet strikes here and smoothly glides over the blade and comes like this. This is the water jet which comes like this. Now, let us consider that the water jet is coming with a velocity V1 in this direction, which is tangent to the at this point V1. This is the direction V1. It comes like this, and as it strikes here, this bucket is moving. The bucket linear velocity of the bucket is u in the same direction. That means the water jet velocity is in the direction of the speed of the bucket. That means the tangential direction. This is the tangential direction. So, this tangential direction is the speed of the bucket, and that is specified at the central plane, as I have told. That means this line, the central line of the bucket. We specify this speed u, which is given by the product of the rotational speed and the radius. Okay. So, this is the u, the radial, this is the linear speed of the bucket. Now, the jet comes out, the water jet comes out through from the bucket gliding over the surface. That means, if we denote the velocity, now the direction of the velocity coming out from the bucket with respect to bucket, if I write the velocity relative to the bucket is VR2 at the outlet, this is divided into two halves VR2. So, we will see VR2 must glide along the bucket. That means, the direction of VR2 must coincide with the angle or the direction of the bucket at the outlet. That means, if I draw a tangent like that to show this angle is theta, known as camber angle of the bucket at the outlet, and this angle, this side the acute angle is beta 2, as we already used that, the angle of the relative velocity with the tangential direction, this angle is beta 2. Then the relative velocity will be with this angle, that means the angle which will make with the tangential direction is beta 2, beta 2. That means, this must glide along the surface. Similar is the case for entrance, that the fluid should enter in such a way that the direction of the velocity relative to the bucket should coincide with the angle or the curvature or the angle of the bucket at the inlet. And this is a very important requirement for fluid machines, that the direction of the velocity relative to the blade at inlet and outlet should coincide with the blade angles at inlet and outlet. Otherwise, what will happen? The fluid will neither glide at the inlet along the blade, nor it will come gliding along the surface of the blade at the outlet, for which there will be unnecessary losses. But it is difficult to have a design of a fluid machines which under varying operating conditions will maintain that. But usually at its rated condition, it is designed in such a way that the angle of the relative velocity must match with the blade angles and outlet at inlet and outlet respectively for the relative velocity. So, therefore, whenever in any problem we will specify the blade angles at inlet and blade angle at outlet, means that this is the angle the relative velocity makes. If the blade angle at inlet given with respect to the direction of motion in the with respect to the direction of the blade motion is beta 1, that means this is the angle of the relative velocity with the direction of motion of the blade, like this. So, they should match each other VR2. Now, with this concept and taking a single cross sectional view of a single bucket, the way the water jet comes, hits it and glides along the surface of the bucket, we can draw now the velocity vector or the velocity triangle. At inlet, the velocity triangle will be like this. This is the V1. Let us consider this is V1. V1. V1 is in this direction. Now, U, the blade velocity is also in the same direction, and here one thing is that inlet and outlet, this is at 1 and this is 2. U1 is equal to U2 is equal to U, because the blade velocity is same at inlet and outlet. It hits here and comes out, as you have seen in the earlier picture, in much clear fashion, much clearly, that inlet and outlet, they do not vary in their radial location. So, U1 U2 is equal to U, and they are in the same direction. So, the vector diagram we just show U as this. So, this part will be the relative velocity at inlet VR1. Well, now we know the definition. Relative velocity is the vector subtraction V1 minus U, and here they are in the same direction. So, VR1 is V1 minus U. Now, the tangential component of the fluid velocity at inlet VW1 is nothing but V1, because V1 itself is in the tangential direction. So, that will be equal to VR1 plus U, VR1 plus U. Well, VR1 plus U. Now, we draw the velocity vector or the velocity triangle for the outlet. For the outlet, we will draw the velocity vector or the velocity triangle at the outlet. Just okay. Now, the velocity vector at the outlet, if we draw, we see this picture, it will be enough. Now, here this is the VR2. So, therefore, here first we draw. Now, we write one thing, that VR2, how to draw the velocity vector or the velocity triangle. VR2 is V2 minus U2. VR2 is V2 minus U2. U2 is U, that is U only here. Now, we draw this U. U is same both at inlet and outlet. Okay. Now, we draw the velocity vector like this. This is direction U, because this was our direction U. This is the direction of U. Okay. So, this is the direction of. Now, this is the direction of VR2 and this is beta 2. This is given by this angle. This angle is beta 2, that is the blade angle at the outlet, and this is therefore V2. And you see, this satisfies this equation. How? Because you can write V2 is equal to VR2 plus U. to check it like that, u plus Vr2 in a sense makes this resultant velocity which is in opposite direction in the triangle, velocity triangle, that vector triangle. So, this is the outlet velocity. Now, here there are certain things to understand. So, this is the outlet velocity triangle. Now, Vr2 and Vr1, the inlet relative velocity and outlet relative velocity should not change, because this will change, I have told, when there is a change in the flow passage, cross sectional area of the flow passage. There is a change in the cross sectional area of the flow passage, but this is an open flow, the flow is open to atmosphere. So, with respect to this bucket, the velocity of the fluid will change because only of the friction. So, in absence of friction or liquid viscosity, Vr2 is equal to Vr1, but because of the friction, if we consider the friction of the blade or the bucket surface, then Vr2 is less than Vr1, and we use Vr2 as some k times Vr1. K is a multiplying factor which is little less than 1. The value is very high, it is in the order of 0.9 or more, because the surface is very smooth and polished. So, therefore, Vr2 is almost equal to Vr1, but there is a reduction in V2, and this is the component Vw2. So, therefore, we see that Vr2 remains almost same, u remains same, it is only the change between V1 and V2 that gives the power, that gives the mechanical energy or head to the rotor. Now, let us write that equation, that head or energy given to the rotor per unit mass E by m, that is the head given to the rotor, which we already Vw1 u1 minus Vw2 u2 by g. Well, and this can be written also to, for an understanding like this, V1 square minus V2 square by 2g. Okay, I write 2g again and again, u1 square u2 square by 2g in general. This is in general, plus Vr2 square minus Vr1 square by 2g. Now, in this case, this is 0, u1 u2, and Vr2 is also equal to V1, Vr1 almost equal to Vr1. This k value is very high, so that there is a loss due to friction only, and if you neglect the friction, it is 0. So, this is responsible only for this equals to this. So, therefore, there will be a reduction in absolute velocity. Now, if we write this Vw1 u1, now Vw1 is V1 Vr1 plus u. So, therefore, let us write Vw1 is Vr1 plus u, Vr1 plus u. Now, what is Vw2? Here we write Vw2 from this triangle trigonometric relation. Vw2 is Vr2 cos beta minus u, Vr2 cos beta 2 minus u. Here beta 1 is 0, that is why I am not using beta 1 the angle, because u is the V is or the Vr1 is same direction here in the tangential direction coinciding with the inlet angle of the bucket. So, that is why it is 0. Now, this component of V2 is in this direction, which is in the opposite direction to that of the Vw1. Vw1 is this one, V1, it is in this direction, and this goes in the opposite direction. This component is in opposite direction, that is direction opposing to the jet velocity. So, therefore, taking the direction of jet velocity or blade velocity, which are in the same direction as positive, this will be minus. So, therefore, we take this as minus. So, this into u, and minus minus plus plus Vr2 cos beta 2 minus u into u divided by g. Okay. So, we can write this. So, therefore, we can finally get an expression that this becomes equal to VR1 into 1 plus, then VR2, if we just write K VR1, K is a multiplying factor which takes care of the friction, K VR1, 1 plus K VR1, VR2 is equal to this U cancels, 1 plus K U, okay, divided by G. G is per unit mass, mg, sorry, per unit weight, per unit weight. Okay. So, therefore, energy added or the head added per unit mass will be, therefore, head added per unit mass will be E by m will be simply V R 1 plus K VR1, VR1 1 plus K VR1 into U. U is the blade velocity. Okay. Now, if we want to find out the total power that is being delivered to the rotor by the fluid, then we have to multiply this head given by the fluid to the rotor into the mass flow rate. And what is mass flow rate? It is rho times, it can be written, the mass flow rate is density into the flow rate Q, that is the mass flow rate. Usually in hydraulic machines we use the nomenclature volume flow rate when the fluid is incompressible. You know, dealing with water we always use the volume flow rate, that is why we are writing rho Q dot instead of m dot. Rho Q dot VR1 1 plus K VR1 into U. Okay. Now, this VR1 we write 1 by Q 1 plus, sorry, K VR1, no, VR1 I have taken common, it is wrong, I have done something wrong here, sorry, K cos beta 2, I am sorry. When we have taken VR1 as common, VR2 is VR1 cos K cos beta 2, sorry, 1 plus K cos beta 2, I am extremely sorry. So, it is 1 plus K cos beta 2, 1 plus K cos beta 2. So, 1 plus K cos beta 2. Now, VR1 again I replace by V1 minus U into U. This is the expression for power delivered to the rotor by the fluid. I am sorry, this will be 1 plus K cos beta 2. Here I did a mistake hurriedly, that U cancel, VR2 is equal to K VR1. When I take VR1 as common, it will be 1 plus K cos beta 2 by G. So, per unit mass it will be VR1 1 plus K cos beta 2 into U. So, total power developed by the rotor or given to the rotor or the wheel by the water jet is rho Q dot into 1 plus K cos beta 2. VR1 again I am writing as V1 minus U into U. This is the power developed. So, this class up to this. Thank you.